Welcome back to this next video in which we are discussing adjoining elements to a ring. Okay, so in this video what we're going to do is formalize the concept of adjoining elements to a ring. Okay, so what we're going to start off with then is some arbitrary commutative ring, capital R here. Okay, and we're going to say that we want to adjoin on a new element to this ring which is going to satisfy a certain polynomial relation, okay, which I'll denote like so: p of x is equal to 0. So to write this out fully, let's say we have some polynomial p0 plus p1x plus all the way up to pn x to the n is equal to 0. Okay, and these pi's are all elements of the ring capital R, so it's an element of the polynomial ring over the ring capital R. Okay, so we have some polynomial here, and I want to adjoin on an element to our initial commutative ring capital R here that is going to satisfy this polynomial relationship. Okay, so what I'm going to do is I'm going to state the formal way that you do this, and then we will spend the rest of the video trying to understand why this is true. Okay, so the way in which you do this is you take the polynomial ring over the ring capital R. So the polynomial ring will say in the indeterminate x over the ring capital R, and you quotient this ring out by a principal ideal, namely the principal ideal which is generated by the polynomial p of x, which we've already agreed is an element of the ring of polynomials over the ring capital R. Okay, so this structure that you end up with, this quotient ring, is going to be your answer. It's going to be your ring extension. Okay, now I should just say that we will be quotienting out by, well, this polynomial p of x that we've chosen here, it will be a non-constant polynomial. Okay, it will be at least degree 1 or greater. Okay, you can do, of course, you can construct the quotient ring for a not a constant polynomial and principal ideal generated by a constant polynomial. Okay, but it doesn't necessarily end up being a ring extension, by which I mean it doesn't end up necessarily containing the initial ring. So we will assume for our purposes here that the degree of the polynomial p of x is greater than or equal to 1. Okay, right. So our task then for the rest of this video is to try and understand why this is the case. Intuitively, why does this actually produce us a ring extension of the ring capital R, which now contains a solution to the polynomial p of x? And I should say it's not necessary for you to actually have a polynomial which doesn't already have a solution in the ring capital R. You can use a polynomial that doesn't contain a that does contain a solution in the ring capital R. It's just that if you use a polynomial which doesn't have solutions in the ring capital R, then you can see, well, it's easier to motivate why you would want to bother doing that in the first place. Okay, right, and it will become more important later on when we go on to field theory and discuss all of this specifically for field theory. Okay, so let's try and understand then why this actually is our desired ring extension. Okay, so the first thing that I want to tackle is the polynomial ring in the indeterminate x over the ring capital R. So I want to give you a new way of viewing this polynomial ring, which is going to be more helpful for us understanding what it has to do with ring extensions in this way. Okay, so this is how I'm going to explain this. Imagine taking the ring capital R here and just adding in the element x, as we did previously in our concrete example. Okay, so imagine adding in, so unioning in the set that contains this element x, okay, the indeterminate, this symbol here that we want to add in. Okay, well, now that you've got x in the ring capital R, you can construct a whole bunch of algebraic expressions involving x, and these expressions look like polynomials. Okay, so for instance, let me take a polynomial which we'll call ax here, and it will be something of this form: a0 plus a1x plus all the way up to, let's say, am x to the m here. Okay, and hopefully what you can appreciate is that this polynomial is actually an algebraic expression involving coefficients from the ring capital R and just this x. You should be able to construct this in this new ring. If we're trying to add in this element x, then you should have an answer in your ring extension where you've added in this element x. You should have an answer for this algebraic expression. You should be able to do this. You should be able to take arbitrary powers of x. You should be able to multiply them all by elements of the original ring. That's what we've got as coefficients here. And you should be able to take linear combinations of those things. You should be able to add them together. Okay, so think of the addition here and the multiplication as addition and multiplication in this larger ring extension that we're trying to construct, which contains the element x. So this is just an algebraic expression which you should have an answer to what this is equal to in your ring extension of the ring capital R, which is going to contain x. Now, a way of viewing the polynomial ring over the ring capital R here is that it is just the ring extension of capital R, the ring capital R, where all of the algebraic expressions of this form, all of these polynomials in x, are all distinct. Okay, so the ring never wraps around, basically. All of these distinct algebraic expressions that you can construct involving elements of the initial ring capital R and this new symbol that you've stuck in, x, all of them are distinct, none of them are the same. Okay, that's what you've got here. You have adjoined on the element x, and then all of the algebraic expressions, you've just constructed them all, and then you've said none of these algebraic expressions are equal to one another, so they all need to be considered as separate elements in this new extension ring that I've created here. And that's what this polynomial ring over the ring R really should be thought of. Okay, and it's going to be very helpful to think of it in that way, as a ring extension of the ring capital R, where all of these algebraic expressions are distinct. Okay, it never wraps round back on itself, unlike our example here. Okay, in our example, we insisted that this polynomial here was going to be equal to 0, so it was not distinct, it wasn't a new element basically, it was actually equal to an element we already had, and that's why this thing ended up wrapping back on itself and you didn't end up having to look at all the polynomials involving this zeta element. Okay, right, so just to confirm this, some people will call the ring of polynomials over the ring capital R, they'll read this as R adjoin x. Okay, so they'll think of it as you have taken the ring capital R and you have adjoined on the element little x here, and then you've just taken all of the algebraic expressions that you can possibly construct. And think about it, all of the algebraic expressions you can possibly construct are of this form. They're polynomials. Okay, so polynomials really are absolutely all of the algebraic expressions you can possibly construct just using ring theoretic operations. Okay, and you've said all of these expressions are distinct, none of them are the same, and so we have to give them all separate symbols, and that's what this is. It's the set of all polynomials in the indeterminant x with coefficients in the ring capital R. And how do we add and multiply polynomials in here? Well, it's exactly the way that you would be forced to if you want this to be a ring. Okay, so if we, for instance, take two polynomials, so let's say we've got a of x and then we've got b of x here, which is b0 plus b1x plus all the way up to, and I'll have to come up with some other symbol for the degree. Let's have m bar, so bm bar, x to the m bar. So these m and m bar are not necessarily the same, so they don't need to be the same degree here. Okay, then how do you add these? If you want to consider what these two added together are equal to, well, we want the addition to obey associativity and commutativity, and we can remember now that all of these things, the addition and multiplication here, you can really think of that as addition and multiplication in the initial, in the final ring extension here. Okay, so if we want to add these together, we want addition to obey associativity and commutativity, so what we can actually do is just regroup it like so. a0 plus b0, so we can bring the b0 next to the a0 basically. Then we can bring the a1x next to the b1x. We also want multiplication to distribute over addition, so we can factor out the x here, so we'll get a1 plus b1 times x, and then it will go on and on and on, and you'll just add all the components up here. Okay, and then you'll go to the term whichever one has the higher degree. Okay, so you just add up the coefficients that are in front of the same power of x, basically. Okay, and that's the only way that this can work if you want this to obey associativity and commutativity and distributivity. Okay, and that's exactly the way that we define addition to work in the ring of polynomials when we defined it very abstractly. Okay, and then multiplication. How does multiplication work? If you want to multiply two polynomials, then all you do is apply distributivity of the monomials. So if you want to multiply this one by this one, you put them next to each other. So I'll write it here. So a0 plus a1x plus all the way up to x to the m here. And we want to multiply that by our polynomial bx here. So we'll have b0 plus b1x plus all the way up to bm bar x to the m bar, like so. And then how are we going to define the way that multiplication of polynomials occurs? Well, remember that you can think of this as addition in our polynomial ring here. Okay, so if we wanted to obey distributivity, there's only one way this can work. You have to multiply this one by every single thing here, you have to multiply this one by every single thing here, and then onwards, and add up all of these terms. And how should the powers of x multiply? Well, of course, if we want to multiply monomials together, how should that work? So if we consider, for instance, am x to the m multiplied by bm x to the m bar, rather, that should be bm bar x to the m bar. Okay, so we want multiplication to obey associativity and commutativity, so we can swap things around, so we can get this to am bm bar here. And then how should we multiply the powers of x together? Well, these are just powers of x. This is just x times x times x m times. This is just x times x times x m bar times. So of course the way that they should multiply together is to give x to the power of m plus m bar. Okay, so really, the way that addition and multiplication work in this polynomial ring is completely and utterly in accord with this really being this extension ring of the initial ring capital R, where you've adjoined on this new symbol, little x here. Okay, so this is starting to make more sense now that we are seeing that this is really like the most extreme ring extension you could ever come up with. Okay, it's where you add in a symbol and then all of the expressions that you can possibly concoct with that symbol are not equal to one another, and you can see that that will be a ring extension of the initial ring R, because the constant polynomials will just add and multiply in exactly the way that the elements of the ring did. So there's a very natural homomorphism from the initial ring into the polynomial ring over the ring capital R. Okay, so this is a ring extension, and this is really the most extreme one you could possibly come up with. Okay, it's the biggest one you could possibly come up with. And now, in a way, what we're going to do is when we say that we want our element x that we're adding in here to obey a polynomial relationship, we are then going to make it so that the ring extension we're going to end up constructing is not as big as this. We're going to make it wrap back round on itself. We're going to make some of these expressions, these algebraic expressions involving the element x that we've adjoined on, equal to something else. We're going to make them equal to 0, basically. And that's what quotienting out by the principal ideal generated by the polynomial p of x in the ring of polynomials is actually going to achieve, but we need to investigate that in more detail. Okay, so let's go over the page and think about this a little bit more. Okay, so I'm going to draw a picture then. So let's have a picture here. So this box is going to represent the ring of polynomials R adjoin x. So I might now use that notation R adjoin x for naming this ring of polynomials. Okay, so I'll colour this box in red here. Okay, and what we're now going to construct then is the principal ideal generated by this polynomial p of x. Okay, so this will be a subset of our ring of polynomials. Now let's have a little bit of a think about what this is actually going to look like. So let's get a little bit of intuition as to what we actually mean by the principal ideal generated by this polynomial p of x. Okay, so whenever you take a principal ideal of any element in a ring, it just means take this element, so in this case p of x, this polynomial, and multiply it by all other elements in the larger ring. Okay, so what we're going to do is we're going to construct the subset which contains all things of the form f of x multiplied by p of x, where f of x is some element of the larger polynomial ring R adjoin x here. Okay, so you're going to go through every single polynomial in the indeterminate x with coefficients in the ring capital R, and you're going to multiply them all with this polynomial p of x. You're going to get all of the answers and you're going to stick them in here. Now let's just get some intuition for what's going to actually end up in this set then. So one of the polynomials that we will multiply with p of x will be the 0 polynomial, and when we multiply the 0 polynomial with p of x, we'll get the 0 polynomial back again. So one of the elements that's going to be in this principal ideal, no matter what p of x is the 0 polynomial. So there it is. Okay. In addition, we're going to multiply p of x by all of the other constant polynomials where c is not the additive identity, so it's not 0, but it's some other constant, it's some other element of the initial ring, capital R. So we'll get all of those in our principal ideal generated by p of x as well. So this is just to give you a bit of intuition as to what's going to be in there. We're also going to get all degree 1 polynomials multiplied by p of x, so we'll get c1x plus c0 times p of x, where c1 and c0 are both elements of the initial ring, of course, they're the coefficients. And then we'll go on, we'll have all degree 2 polynomials and degree 3 polynomials and degree 4 polynomials multiplied by this polynomial p of x. And we'll get all of these answers and stick them into a set, and that's what I mean by the principal ideal generated by p of x. Okay, so what we now want to consider then is what do we actually end up with then if we quotient out our ring of polynomials in the indeterminate x over the ring capital R by this principal ideal generated by px, and why does that actually fulfill what we were trying to do? Why is that actually going to be a ring extension which has an element that actually satisfies the polynomial p of x? Okay, well, intuitively, why does this stand a chance of doing what we actually want it to do? Well, remember, we want this polynomial p of x, we want this algebraic expression involving this new symbol x to be equal to 0. And we have absolutely bluntly done that now, because of course an element that will always be in the principal ideal generated by p of x is p of x itself. Okay, so we have effectively made p of x and 0 equivalent by putting them now into a principal ideal together and saying that we are going to quotient out the ring of polynomials by this principal ideal. Okay, because remember, when we quotient out by an ideal, what we effectively do is partition the ring up into cosets of the ideal here, and then all the elements that are in a coset, and of course the ideal itself is one of these cosets, are declared to be equivalent to one another. They're now just one element in a new quotient ring. So effectively we are making all of these elements equivalent. We're making p of x equivalent to 0, and we're making all multiples of p of x, all polynomials in our polynomial ring that are expressible as multiples of p of x, they are all being declared equivalent to 0 as well. And that's exactly what we want to do, because we do want all the other polynomials that are just multiples of p of x to be made equivalent to 0, because of course they will be equal to 0, because if they're just multiples of p of x and p of x is 0, then they'll be 0. So this is exactly what we want to do. Intuitively, going back to our concrete example, it's like saying that anything that has a multiple of this expression in it, any other higher expression involving powers of zeta which has this in it, will be just declared to be equal to 0, and of course that's going to be the case, okay, because if it's multiplied by this is declared to be equal to 0, so of course when 0 multiplies what's left over, the quotient portion, you will just end up with 0. So that seems fairly logical. Now then, let's think about actually what's going to happen when we partition up the polynomial ring by the cosets of the principal ideal here. Okay, so what we'll end up doing is quotienting out our ring of polynomials here by our principal ideal generated by p of x, and this is under-exaggerated. You'll probably end up with an absolutely enormous number of subsets in your partition. Okay, but for the basis of the picture, I have drawn 4. Okay. Right, so now let's just think about what a coset will actually be like. So if we have some polynomial a of x that's in one of these cosets, then what will the coset of the principal ideal of p of x under this element a of x actually look like? Well, of course, it will be all things of this form. A of x rather, this polynomial that's in this coset, plus something that's in the ideal. Okay, remember it's an additive coset of the ideal here. Okay, so it'll be plus something that's in the ideal. All things that are in the ideal are of the form some f of x times p of x. Okay, so basically all elements that are related to one another by having some multiple of p of x added onto them are all going to be put into a coset and made equivalent. Okay, so all the elements that are related to one another just by having a multiple of p of x added onto them are going to be made equivalent. Right, so if you want to know whether two elements are equivalent to one another and are being put into a coset with each other, just ask, is the sum multiple of p of x that I can add onto one to make it equal to the other? Okay, and this is also looking very intuitive because we do want elements of that description to be made equivalent to one another, because remember this portion, this multiple of p of x is just going to be equal to 0. Okay, so effectively if you have some huge great algebraic expression, okay, so let's say you've got some massive great polynomial, so let's say b of x is a massive great polynomial, huge great thing, okay, then what we would like to do is split it into some multiple of p of x plus something that's much smaller. Let's say a of x is much smaller, okay, a little remainder term here, and then what we can say is b of x will be in the same equivalence class as this much simpler polynomial a of x, okay, because it's related just by a multiple of p of x here. Okay, right, so that's what we're going to do then. We're going to quotient out by our principal ideal generated by p of x in this way to get this bunch of cosets of the principal ideal generated by p of x. They're all going to go into a set together. So remember, this quotient ring here will just be the set of cosets. You'll stick all of the cosets into a set, and they'll now be your elements here, okay? And I claim that this is actually going to be a ring extension of the ring capital R, and that it's going to have a solution to the original polynomial p of x here. Okay, so what I firstly want to show you then is that it actually is going to be a ring extension of our ring capital R. So I want to firstly show you that R is going to be a subset of this structure here. Okay, so this is going to rely on the fact that I said we were going to take p of x as a polynomial that had degree greater than or equal to 1, i.e. it wasn't some constant polynomial. You can of course construct this thing for a principal ideal generated by a constant polynomial, but then it is probably not going to be the case that the original ring will be a subset here. Okay, right, so now how can I show this then? So my claim is that all of the elements of the original ring, okay, or rather their correlates in the polynomial ring, which are just the constant polynomials, my claim is that they will all end up in distinct cosets, okay? And why can I make that claim? Well, the reason that none of them are going to be in the same coset as each other is because how can you possibly write a constant polynomial plus some multiple of p of x is equal to another constant polynomial? So think about this. If I've got two constant polynomials, a and b, okay, so these are just two different constants, then if they were in the same coset, then that would mean I would have to be able to take some multiple f of x times p of x and add it to a to make b. Now that's not possible if p of x has degree greater than or equal to 1, because this thing is always going to end up having degree greater than or equal to 1, except for that silly case where f of x is equal to 0. But in the case that f of x is equal to 0, you do nothing to a, you add on 0, and therefore the answer will just be equal to a. But in all other cases, this will end up having degree greater than or equal to 1, and therefore you'll end up with a polynomial of degree greater than or equal to 1, not another constant polynomial. So my message here is that all the constant polynomials, providing that this polynomial has degree greater than or equal to 1, are going to end up in distinct cosets, okay? and therefore we will be able to form a very natural map from the initial ring into here, and therefore we can think of it as a subset of this. Okay, and indeed addition and multiplication is going to be exactly as it was here because of the way that we define addition and multiplication on the set of cosets just by picking representatives and multiplying them together. And remember, multiplication in the initial ring of polynomials here, R adjoin X, was completely compatible with addition and multiplication here. So in this quotient ring it's still going to be compatible. So I hope you understand that this initial ring that we had here is still going to be contained within this quotient ring that we've produced here. So it is a larger ring that contains our initial ring, capital R, provided, as I say, that that polynomial p of x is degree greater than or equal to 1. Okay, now the second part that we need to think about then is, does it have a solution to the original polynomial that our initial ring might not have had a solution to? Okay, is x a solution to the polynomial? Well, of course, x will be in one of these cosets. So let's say it's in this coset here. Okay, so x is in this coset here. So this is the coset that contains x. So we could call it x bar here, the coset that contains x. Okay, so x is a polynomial, so it will be in a coset. So now if we consider what this coset put through that polynomial expression is actually going to give. Okay, so if we imagine taking the polynomial expression p of x bar, and this polynomial expression still makes complete sense because, as I say, all of the coefficients that are from the ring are still in this quotient ring here. Okay, so the polynomial expression still makes complete sense, and what we'll end up with, of course, is some algebraic expression involving x bar here. But how do we work with x bar? We just take a representative, okay, and then take the coset that contains the answer. So we could just say this is going to be p of x, so we'll take the representative x, we'll substitute that in for x bar here, we'll work out the algebraic expression in the initial polynomial ring here, and then we'll take the coset that contains the answer. Okay, because that's exactly how addition and multiplication work in quotient rings. That's the way we define it. We say take a representative from your coset, use that in the algebraic expression, and then take the overall coset that then contains the final answer. Okay, so we work out p of x in the initial polynomial ring, and then we take the coset that contains that. Okay, and of course the coset that contains p of x in the initial polynomial ring is exactly the same as the coset that contains 0. It's in the principal ideal generated by p of x. Okay, so here p of x bar will equal 0 bar, and that's exactly the polynomial relation now satisfied. Okay, so there is a solution to this polynomial relation. The coset that contains the polynomial x is going to be the solution to your original polynomial equation. So this is a ring extension of the initial ring, which now contains a solution to the initial problem, okay, which was this polynomial, and it will be much, much smaller than that polynomial ring was, which we could initially think of the bluntest, most extreme ring extension where nothing folded back on itself. All the algebraic expressions were distinct elements. Okay, in this new thing that we formed, loads of the algebraic expressions are now equivalent to one another. Okay, so we will have a break here, and in the next video what we'll do is explore this in more detail. Okay, now what we want to try and do then is characterize the ideals that we're actually, the cosets of the principal ideal that we're actually going to get in one of these ring extensions here. Okay, now this is most easily done if the ring in question is actually a field. So we'll start off there, and then we'll discuss what happens if we're dealing with a more general ring.